Good morning, or I suppose wherever you are, whatever time of day it is. AP Calculus students, Mr. Ford here with another tutorial of the summer packet that I've assigned. And today we're looking at topic C, graphs of common functions. Now this block of text here, I gotta be honest, I borrowed this summer packet from a different teacher. We don't necessarily use the TI Nspire calculator, although this teacher who I collaborated with does use the Nspire for everything. We tend to use the 84, which I have right here in my hand, and I have a classroom set of, so you can use one of mine, or if you have your own, that's always a good idea too. If you would like to purchase your own calculator, the Nspire is a good thing to do. The 83, 84 family of calculators has always been the standard. It probably will be for a while. Or, honestly, Desmos does a really good job too. And Desmos does have an app that you can install on your phone. That is free. You can install on your phone. It's important to have a graphing thing of some ability for you to use. Some sort of machine that graphs things. Whatever you're going to use. Keep in mind that on the actual AP test, you will not be allowed to bring your phone in the room, so you should have some sort of calculating device that can do that. However, today, you don't actually need a calculator. I just wanted to take the opportunity at the top of this video to talk about them. I have, of course, debuted Calculator Cam here in these videos, which I often use to show specific calculations or specific things that are happening on this calculator. But for now, we're just going to keep this down in the corner unless we absolutely need it. So we're going to do most of these by hand and think about these graphs. So today we're just going to graph a bunch of functions. These are graphs that I don't like to use the word should because it's got kind of a punishment thing to it. But these are graphs that I want you to be really familiar with going into the course. Let's start with an easy one, y equals x. So this is literally finding the points where x and y have the same coordinates. So 1 and 1, 2 and 2, 3 and 3, 4 and 4. All of these points have an x and a y that are exactly the same, including the negative ones. Negative 2, negative 2. The x and the y values are the same. And so you get this cool diagonal line that goes through all of those points. When we are graphing an equation, what we're literally doing is finding the points that make the equation true and highlighting them with our pen or whatever. So there you go. There's the first one. Should be noted, this is exactly a 45-degree angle. Not super important for now, but probably is worth mentioning. Or, since we're in AP Calculus, pi over 2. The same thing, but whatever. Okay, next graph. X squared, another really common graph. One thing you want to note about this is that it never goes negative. It's always positive. 0, 0, 1, 1, and then 1, 4 are the points that we're kind of, we want to be aware of. Or sorry, 2, 4, my fault. Like that. You take the x value and square it. When you go over to the left side, negative 1 squared is positive 1, and negative 2 is squared is positive 4. So you get this easy parabola shape like this. And what's interesting about this, you'll soon learn in calculus, is that slope is not really a thing on this graph because the slope itself is constantly increasing. So right here it's horizontal, but then it gets to be pretty vertical pretty quick as you move along the graph like that. But we have lots of time to talk about that in calculus. Let's keep talking about things that we should be aware of. Graph number 3, x to the third power. This graph can go negative. The three key points are negative 1, 0, 0, and 1, 1, which makes you think that it's going to be a straight line. It's not, though. The next point, which will not fit on this graph, is the point 2, 8, which I suspect is probably up here somewhere. 2 to the third power is 8, and then you have 2, negative 8, which is all the way down there, which gives you kind of this S-looking shape graph like this. Kind of like that. Next, we have the square root of x, which we talked about in the last video while I'm dealing with domain and range. You'll notice that this graph has nothing going on over on this side. There is nothing over here because you cannot take the square root of a negative number. The first point is 0, 0, followed by 1, 1, and then kind of the opposite, because this is an inverse graph of x squared. There is kind of an inverse relationship. That's another topic that we will deal with later on in this series. But there's an inverse relationship. So what you're doing here is you have the same graph turned on its side. Actually, I kind of missed one of the key points there. 2, 4. Or sorry, 4, 2. It's worth mentioning that the points here are the same points as up above, but flipped. And you cannot do the negative half of the graph because it wouldn't be a function then. You'd have to add on a negative square root of x to get it to work. So, okay, let's talk about absolute value of x. Absolute value, like many topics in calculus, absolute value gets a big glow up when you get to calculus. Things that you've dealt with in Algebra 1 or whatever suddenly become really, really, really important. But the nice thing is they're really easy too. Absolute value of x basically takes the same graph we made in number 1, and as long as x is positive, nothing changes. But as soon as you go into negative territory, the absolute value starts returning positive answers. So negative 1 gives you positive 1, negative 2 gives you positive 2, negative 3, and so on. And so you get this V-shaped looking graph like this. There you go. Another topic we'll talk about later on in this series is how to take this graph and shift it left and right and up and down. We'll talk about that later on. Now we have an interesting case. This is one that pops up on the AP test all the time. Absolute value of x over x. You've probably never thought about this graph before, but let's think about it right now. There's kind of two ways I want to think about this, almost like a piecewise function. As long as x is greater than 0, I guess you could say including 0 on that one. Actually, 0 doesn't exist in this graph. X can't be 0. The domain in this graph is that x cannot be 0. As long as x is greater than 0, you're going to get a positive number divided by its positive self, which means you're going to get 1. This graph always returns a value of 1 as long as you are talking about numbers that are greater than 1, like that. 2 over 2, 3 over 3, 4 over 4. These graphs all return 0. These points all return 0. Keep in mind, I got an open circle right there. That's because you cannot plug 0 in. There is no function value if you plug in 0. It does not exist. There's a hole in the graph. So put an open circle there because there is not an answer. Now, what happens if you go negative? You get the same behavior, but what happens is that this number is always positive, but that number now becomes negative. So, for example, negative 1, you have the absolute value of negative 1 divided by negative 1. Well, that's positive 1 over negative 1, which is negative 1. The same thing happens with pretty much every other number. You get positive 2 over negative 2, which is also negative 1. So this graph returns negative 1 if x is less than 0. So thinking about this like a piecewise function is a really good idea. Again, I'm going to put a big open circle because there is no function for 0. But down here, it looks like this. Oh, if you can draw it correctly without moving your tablet like that. This graph shows up all the time in AP Calculus, so something to be ready for. We have x to the 1/3 power, which I want to point out is the inverse. Another topic, again, we'll talk about this later. It's the inverse of y equals x to the 3rd power. So it's got a lot of the same things. It's basically the same graph, just rotated 90 degrees. 0, 0 still on this graph. 1 to the 1/3 power is still 1, and negative 1 to the 1/3 power is also still negative 1. Keep in mind, this can also be written, by the way, as y equals the cube root of x. Same thing. Now, this is going to basically do the opposite of the other function. Instead of 2 going to 8, 8 is going to go to 2 because the cube root of 8 is 2. So we're going to have a point way out here. That point is 8, 2. We're also going to have a point way over here on the edge of your paper, which is negative 8, negative 2. So you get the same kind of graph shape, but it's turned on its side. Kind of like that. Graph 8, x to the 2/3 power. Okay, this is interesting. Now, if we're doing this without a calculator, that adds some extra challenge to it. So, one big part of AP Calculus is that every question is kind of classified as either with calculator or without calculator. So this one, we're doing without calculator. But here's what I want you to think about. This is the same graph we just made, x to the 1/3 power, but now it's squared. If you break up the 2/3 power into 1/3 times 2, we can think about this maybe a different way. One thing that's important, because of the second power, this is always going to be positive. So let's think about some key points along the way. 0, 0 is going to be on this graph. 1 to the 1/3 power is still 1, and 1 squared is still 1. So 1, 1 is on the graph. Negative 1 to the 1/3 power is negative 1, but negative 1 squared is positive 1. If you try, the next whole number answer would be 8, I suppose. 8 to the 1/3 power is 2, and 2 squared equals 4. So 8 gives you the number 4. And if we put that point, it's going to be kind of way out here, 8, 4. And also negative 8, positive 4 is going to be way over here, negative 8, positive 4. So this graph kind of looks like this, if you start connecting it. It's got kind of interesting like bird wings effect to it. Kind of cool. Okay, now we enter into the trigonometric portion of today's program. You guys are coming out of pre-calc. You know, we're asking you to do your best with this stuff. It is going to be spiraled into the curriculum, so you will continue to review your sine, cosine, tangent stuff as we go on. Sines start at 0, 0. They go up to 1. They cross through 0 at pi, down to -1, back up to 2 pi. So you get a classic sine wave happening like this. Whoops, if you can draw it without bumping your tablet. And the same pattern repeats over here. Honestly, for for calculus, you don't need to know super amount about sines and cosines, other than they are periodic functions, and you want to be familiar with your key unit circle values, but we'll have lots of time to talk about that in later topics. Cosine does the same thing, but it starts at its maximum, at 1. Always, whenever you're looking at sine and cosine, you should always be thinking about the unit circle. Cosine is the x value as you rotate around this circle. 1, 0. At pi over 2, it's to 0. At pi, it's -1, back to 0, back to 1. So like this. Always think about your unit circle as you are doing your trigonometric graphs and any function involving trig. Tangent has an interesting thing going on. Again, tangent is defined as the sine over the cosine. So we could compare the sine cosine graphs. Basically, if cosine is 0, then tangent is undefined. So whenever cosine is 0, that happens at pi over 2, 3 pi over 2, negative pi over 2, and negative 3 pi over 2. You can go ahead and put asymptotes at those points because that is where your tangent graph does not exist. Similarly, if sine is 0, then tangent is equal to 0. So that happens at 0, pi, 2 pi, negative pi, and negative 2 pi. You might be familiar with the shape of this graph at this point, where it goes kind of like this. It has these little S shapes in the middle. Honestly, we could spend a lot more time, if this was a trig course, we could spend a lot more time talking about why this graph does what it does. But again, the whole point of this topic is for you to be familiar with it so that you have an idea of what to do when you're encountering this problem. Cotangent does the same thing, but it's flipped. Now, it's cotangent is defined as cosine divided by sine. So now it's the same rules. Whenever sine is 0, you're going to have an undefined. So you're going to have asymptotes on the whole number pi values. So there's an asymptote here, and an asymptote at negative 2 pi, and positive pi, and positive 2 pi. And cosine is where your zeros are. Anytime cosine is 0, the cotangent is 0. So you have zeros here, and here, and here, and here. The other tricky thing about the cotangent graph is that the S shapes are flipped backwards. So your S's are going to look like this. What's going on here is that as you approach certain values of the sine, like for example, as you approach, let's say 0, for example, as you approach 0, your cosine is getting closer and closer to 1, but your sine is getting closer and closer to 0. So what's happening is that you have a number pretty close to 1, let's say 0.99, being divided by a number pretty close to 0, like say 0.01. And what turns out is that this is a very, very large number. It's actually 99. So what's happening is that as you get really close to those points, you're actually shooting your value up to infinity like that. So again, we could spend a lot more time talking about why this graph does what it does, and there's some important calculus conversations to be had there, but for now, we're just being familiar with graphs. Now, secant and cosecant. Somewhere in your head, secant is 1 over the cosine of x, and cosecant is 1 over the sine of x. So basically what you need to do here is think about, okay, where is the cosine equal to 0? Because wherever the cosine is 0, this thing is undefined. Cosine is 0 at the pi over 2's. So much like the tangent graph up above, we're going to put our asymptotes down at the pi over 2 points. And if cosine is 1, then we're going to have a point that's 1. So cosine is 1 or -1 at the whole number pi. So we're going to have a point here and a point at -1 for pi, a point at 1 for 2 pi, and then we follow that same pattern backwards. Now what's interesting here is that since cosine only ever returns a number between 0 and 1, cosine of x has a range of -1 to 1. If you divide 1 by a number in this range, you're always dividing it by a decimal, which always makes it bigger. So these are the smallest values these can be. That's why you usually get these U shapes that you see. These graphs they look like parabolas. They're not parabolas because they are straight-sided, but you get the idea. Again, I don't mean to condense your entire trigonometry class down into one 15-minute YouTube video, but cosecant has the exact same thing happening. Sine is 0 on the pi's, so we'll put our asymptotes down just like before. Because whenever sine is 0, the cosecant will be undefined. And then again, whenever sine is 1 or negative 1, this fraction will be 1 or negative 1. So pi over 2 is 1, 3 pi over 2 is negative 1, negative pi over 2 is negative 1, and negative 3 pi over 2 is positive 1. And then you can fill in your U shapes once again, like this. The joke in trig and pre-calc is that these graphs always look exactly the same. The only difference is that where the actual values on the x-axis are. So it's important to take a minute to ponder. I know that trig and pre-calc is the thing that's the most fresh right now for you, but this is the thing that you should be familiar with these graphs. And again, I don't like to use the word should because it's got kind of a punishment notation or in thing to it, but just keeping that unit circle in mind. The unit circle is the key to everything trigonometric. Always remember your unit circle. We have lots of time to talk about that this year. All right, let's talk about some other common graphs you should be familiar with. There I go again with the word should. You want to be familiar with these graphs. E to the x. Every exponential equation looks basically the same. E to the 0 power is 1. E is, for all intents and purposes, it's about 2.718. We will talk about what E is and why it's important in this class because calculus finally has the tools to explain what E is. But for now, we're just going to, it's about 2.718. So there's a point right about here. Right about here. And then from there, the exponential graph looks pretty much the same as every other exponential graph. Remember, the exponentials can never return 0. They can only approach 0 as you get further and further negative. So you get a graph that looks kind of like that. Natural log of x, I think, again, we're going to talk about inverses at a later topic, but it is the inverse of y equals e to the x. These are opposites, a very important thing that we'll talk about in this class a lot. Basically what that means is that you can take any ordered pair and flip it to make this graph happen. So whereas this graph had 0, 1 on it, this graph has 1, 0. This graph also has, 2.7181 right about there. And the graph will look something like this. Remember, as we discussed in the last topic, all logarithmic functions have a domain of x greater than 0. It cannot be negative. This includes natural logs. A natural log is just a log with a base of e. So it's the same thing. Very important in calculus. We'll talk about it a lot this year. Don't panic about it. Lots of time. Let's talk about y equals 1 over x. Another really popular, this is actually my personal favorite function here, 1 over x. It gives us a chance to talk about a lot of big calculus ideas. What happens is that x cannot be 0, but we're really curious about what happens as you get close to 0. Because when you divide 1 by a number like, say, 0.01, you end up getting 100 as an answer. That's why the graph does this, has a vertical asymptote right there. It does go through the point 1,1. But then as values of x get very large, like 1 over 100, this is basically 0.01. So the graph does this thing, like that. It's got a vertical and a horizontal asymptote. As soon as you hop over 1, you get the same thing happening. It immediately drops down negative infinity, comes back up, passes through -1, -1, and then goes over here like this. A lot of talk about what's happening as you approach certain numbers. That's a very calculus thing to do on this graph. 18 is y over x. I suspect this is a typo on this page, but I mean, if you really want to graph it again, you can. It's the same graph as it was before, but it might be helpful just to remember what that looks like. I suspect there's something missing here, though, so that's okay. 1 over x squared is going to do the same thing as the graph up above, but now you have a number on the bottom that's always positive. So we have to keep that in mind. The same effect is going to happen on the right, where x is greater than 0. You're going to get the same basic, exact same graph. It's going to be a little steeper because the numbers are going to get bigger faster, and they're also going to get shallower faster. I don't know how you accurately draw that with a pen, but it's basically the exact same graph. The difference here is that when you go to the left side, now you're dividing by a positive number. So you're going to get kind of this volcano asymptote. That's what I like to call that. It's got to go through negative 1, 1. So I call this a volcano asymptote because of the behavior with the way the graph looks like that. Number 20, y equals 2 to the x, is going to look pretty much exactly like y equals e to the x over in the top left corner. It's basically the exact same graph. 0, 1 is still on this graph because anything to the 0 power is 1. And 2 to the first power is 2. 2 to the second power is 4, if you want to add that point on there. 2 to the 1/2 power is going to be the square root of 2, which is like 0.7 or something. And that pattern just continues. It looks exactly the same as every other exponential graph. Every exponential graph goes through 0, 1, has this asymptote over here on the left side, and then goes up to infinity very quickly. So they all look pretty much the same. The only difference is how fast or how slow they do that. If you look at 17 and 20, or sorry, I guess 15 and 20, they look pretty much exactly the same. The only difference is that they don't go up as fast, but they're basically the exact same idea. 2 more to handle. 21 is another example of something that happens all the time in calculus. We talk about these kind of graphs. You really got to think about what the domain is here. When is 4 minus x squared greater than or equal to 0? You got to be careful on this one. What this would mean is that 4 is greater than or equal to x squared. So let's really think about that for a minute. X squared, well, here's the thing. If you want to solve this by algebra, what you got to do is put a plus and minus in front of this. This is me, x is less than or equal to plus and minus 2. Like that, if you want to take the square root. And what that means is that x basically has kind of a lower end and a higher end. X has to be less than or equal to 2, but also x has to be greater than or equal to negative 2. Any number in between this range, if you square it, gives you a number that is at least is less than 4. But as soon as you go outside of that range, you know, above 2 or below negative 2, if you square those numbers, the number gets bigger than 4, so it's not acceptable here. So this means that our graph starts at negative 2, 0, and ends at positive 2, 0. And if you try plugging those numbers into the graph up here, you'll see exactly that thing happens. What's interesting here is what happens when x is 0. If x is 0, you get the square root of 4, which is 2. So y equals square root of 4 minus 0 squared. Y is equal to 2. And so you get this. You might recognize this graph from a different math class. This is actually the equation for a circle. Usually with a circle, you'd have to have a plus or minus on this. Because this is positive, it's just the top half of the circle. That's what this graph looks like. In order to make the full circle, you have to put a plus or minus on there and graph the negative half also. But that's what this graph looks like. The sooner we can make the connection between this graph is a semicircle, the better. You'll see these kind of graphs all the time. Semicircle is the signal there. And over here we got sine of x over x, a graph that we should be familiar with. This is one that you might actually need a calculator for, and I wouldn't blame you for that. We could put it together by hand. Let's say, for example, we made a table of values. Let's start at 0, for example. Well, sine of 0 is 1. Actually, this is undefined. But there's going to be a hole there. I think that's worth mentioning too, because the sine of 0 is 0, and on the bottom 0 is 0, so you have a hole in this graph. You know, honestly, the more I think about it, this is probably best if we just grab a calculator and take a look at this one. This is one that I'm not thinking we can put it together with a table. I think we should just look at it. So we're going to graph the sine of x over x on our calculator really quick. We will get really familiar with this. I'm going to use, in the zoom menu, I'm going to use ztrig, which is option 7. I'm pushing the zoom button, which is right on the bottom, right there, middle of the top row. This will give us a window that looks just like ours right here. What this graph does is an interesting thing. It comes up towards 1. Now keep in mind that this graphing calculator cannot graph the hole that we know to be right there. So let's put a hole at 0, 1. And then we're going to kind of make this just fit. Pi is what you're seeing, I think. What's the window here? Oh, look at the table here. Second table. Oh, shoot. What's going on at pi over 2? Sorry, I'm going dead right now. I'm brain dead. I'm setting my table up to count by pi over 2s. Oh, yeah, it is. Pi is 0. And negative pi is also 0. So what this graph does is it kind of has this whole like thing where it comes up towards that graph and then comes up towards that point 0,1 and then does that thing right there. This is an interesting graph. We'll talk about it a lot early on in Chapter 2 of this class when we start talking about limits. We will definitely go over this and a couple other key trigonometric graphs. But for now, this is one that you might actually need a calculator for. I'm trying to think of a way you could graph it by hand, but there it is. That is the final graph for this section, and that takes care of our simple graphs. These are all of them graphs you should be familiar with. Again, I don't use the word should, but you'll be great going through this and taking a look at some different kind of key mathematical ideas. Get yourself a graphing calculator. You can borrow one from me if you need it. My third hour class is about to arrive. You guys are awesome. I'm so proud of you for even choosing to take this class. I can't wait to work with you in the fall. You're going to have a great summer, and I'll see you when you're ready. I'll see you in the next video.